Hello everyone. 你好，你们好，
我很好，你呢？
我也很好，谢谢。The objective of this chapter is to introduce the concept of software architecture and architectural design. Normally, after reading this chapter, we will understand why the architectural design of software is important. We will understand the decisions that have to be made about the system architecture during the architecture design process. And we will also be introduced to the idea of architectural patterns, well-tried ways of organizing system architectures, which can be reused in system designs. We will also know the architectural patterns that are often used in different types of application systems, including transaction processing systems and language processing systems. These are the objectives of our sixth chapter. Now we'll see the topics covered in this chapter. We'll have the first topic, architectural design decisions, architectural views, architectural patterns, and application architectures. Now we'll see some more detailed instructions in introductions of this chapter. At first, architecture design, it is a process, architecture design is a design process for identifying the subsystems making up a system and the framework for subsystems control and communication. You see here, architecture design, it is concerned with understanding how a system should be organized and designing the overall structure of that system. As we have seen in the second chapter, in the model of the software development process, architecture design, it is the first stage in the software design process. It is the critical link between design and the requirements engineering. Also, it identifies the main structural components in a system and the relationships between the components. Pay attention, the output of the design process is a description of the software architecture. And with the architectural design or architectural model, we describe how the system is organized as a set of communicating components. For architectural design, especially in agile methods, agile processes, we have, generally, we think that an early stage of the development process should be concerned with establishing a novel system architecture. So architectural design is always considered as an early stage of the system design process. As we know, for agile methods or agile processes, we have incremental development of architectures, and it is not usually successful when we have to refactor components in response to changes. It is usually relatively easy, but if we need to refactor a system architecture, it is much more expensive. The architecture design, it represents the link between specification and design processes. It is often carried out in parallel with some specification activities. In practice, between the processes of requirements engineering and architectural design, there is a significant overlap. Ideally, a system specification should not include any design information, but this is unrealistic except for very small systems. Architectural decomposition is usually necessary to structure and organize the specification, That's why we say it is often carried out in parallel with some specification activities. Therefore, it involves identifying major system components and their communications. As part of the requirements engineering process, we may propose an abstract system architecture where we associate groups of system functions or features with large-scale components or subsystems. We can then use the decomposition to discuss the requirements and features of the system with stakeholders. Here, this figure shows an abstract model of the architecture for a packing robot system. And this figure shows the components that have to be developed. You see, this robotic system can pack different kinds of objects. It uses a visual component to pick out object. We use a visual component to pick out objects on a conveyor. And then we identify the type of object. We select the right kind of packaging. The system then moves objects from the delivery conveyor to be packaged. It places packaged objects on another conveyor. This architectural model shows these components and the links between these components. You see, that's the actual architectural design. And normally we can design software architectures at two levels of abstraction. We call them architecture in the small. That means we are concerned with the architecture of individual programs. At this stage, or at this level, we are concerned with the way that an individual program is decomposed into components. Another level of abstraction is architecture in the large. Here, we are concerned with the architecture of complex enterprise systems that include other systems, programs, and program components. These enterprise systems, they are distributed over different computers. And these computers may be owned and managed by different companies. This situation is often with very complex systems. In fact, individual components implement the functional, like here, the individual components implement the functional system requirements, and the non-functional requirements depend on the system architecture, the way in which these components are organized and communicate. In many systems, non-functional requirements are also influenced by individual components, but there is no doubt that the architecture of the system is the dominant influence. And generally, we think there are three advantages of explicitly designing and documenting software architecture. The first advantage is that for the stakeholder communication, the architecture is a high-level presentation of the system that may be used as a focus for discussion by a range of different stakeholders. That's why we say here, we may use architecture as a focus of discussion by system stakeholders. The second advantage is that for system analysis, it means that analysis of whether the system can meet its non-functional requirements is possible. Here, making the system architecture explicit at an early stage in the system development requires some analysis. And architecture design decisions have a profound effect on whether or not the system can meet critical requirements such as performance, reliability, and maintainability. So that's why we say explicit architecture is good for system analysis. The third advantage is for the large-scale reuse. A model of a system architecture is a compact, manageable description of how a system is organized and how the components interoperate. The system architecture is often the same for systems with similar requirements and so can support large-scale software reuse. Yeah, that's why here we say that the architecture may be reusable across a range of systems, and product line architectures may be developed. And as we have said before, reuse, yeah, just like in object-oriented programming, reuse is a good way to improve the efficiency of our system development. Now we'll see the architectural representation. System architecture. We often model it using simple block diagrams, just like in our previous figure to show the robot system. We see that simple informal block diagrams show entities and relationships are the most frequently used method for documenting software architectures. As shown in the figure, each box in the diagram represents a component. Boxes with boxes indicate that the component has been decomposed to subcomponents. Yeah, I think it's better to see it like this here. Yeah, you see. Each box in the diagram represents a component. And the boxes within boxes, they indicate that the component has been this big component has been decomposed to subcomponents. And errors here, they mean that data or control signals are passed from component to component in the direction of the errors. We see that, yeah, this way, simple block diagrams have been criticized because they lack semantics. They do not show the types of relationships between entities nor the visible properties of entities in the architecture. That means, as shown by the figure, block diagrams present a high-level picture of the system structure. People from different disciplines who are involved in the system development process, we can readily understand. However, with this widespread use, we say that these informal block diagrams to describe an architecture may be poor architecture representation. I said here, they show neither the type of the relationships among system components nor the components' external visible properties, and depends on the use of architectural models. The requirements for model semantics depends on how the models are used. Here, as we say, the apparent contradictions between practice and architectural theory arise because there are two ways in which an architectural model of a program is used. Now we'll see these two ways in which an architectural model of a program is used. The first one is as a way of facilitating discussion about the system design. As said here, a high-level architectural view of a system is useful for communication with system stakeholders and project planning because it is not clustered with detail. Stakeholders can relate to it and understand an abstract view of the system. They can then discuss the system as a whole without being confused by detail. You see, it's like what we have said before. One advantage of explicitly designing and documenting software architecture is the stakeholder communication. It's the same principle as this way in which an architectural model of a program is used. Here, this architectural model identifies the key components that are to be developed, so managers can start assigning people to plan the development of these systems. The second way in which an architectural model of a program is used is as a way of documenting an architecture that has been designed. Here, the aim is to produce a complete system model that shows the different components in our system, their interfaces, and their connections. For this one, as we have a detailed architectural description, it will be easier to understand and evolve the system. That's why we say, to produce a complete system model. When we have the architectural models, we can document this architecture, and then it will be easier to understand and evolve the system. You see, here are the two ways in which an architectural model of a program is used. We had an introduction to the architectural design. Now we'll talk the decisions of architectural design in detail. We say architectural design is a creative process. That means, when we talk about creative, that means it will have many different possibilities. So the process differs depending, the process can be different depending on the type of system being developed. However, a number of common decisions span all design processes, and these decisions affect the non-functional characteristics of the system. Here, we have talked about the architectural design, where we can design our system organization. And normally we needed to be satisfied. We needed to satisfy the functional and non-functional requirements of a system. As it is a creative process, that here the activities within the process, as we say, it depends on the type of system being developed. Also, it depends on the background and experience of the system architect and the specific requirements for the system. Therefore, it is useful to think of the architecture design as a series of decisions to be made rather than a sequence of activities. That's why we call it also architectural design decisions. In fact, during the architectural design process, system architects have to make a number of structural decisions. And these decisions will profoundly affect the system and its development process. Based on the knowledge and experience of architects, they have to consider several fundamental questions about the system. As some questions like this: is there a generic application architecture that can be used? That means, is there a generic architecture that can act as a template for the system being designed? If yes, then we can use the template directly. Second question is, how will the system be distributed? As we may distribute the system across different cores or processors. So this question, how the system will be distributed, is also an important question to lead the decision. The third question is, what architectural patterns or styles might be used? What kind of architectural styles are appropriate? And the fourth question is, what approach will be used to structure the system, especially the fundamental approach to structure the system. Then the fifth question, how will the system be decomposed into modules? How will the structural components in the system be decomposed into subcomponents? We have the sixth question, what control strategy should be used? What strategy will be used to control the operation of the components in the system? How will the architectural design be evaluated? How should the architecture be documented? How should the architecture of the system be documented? All these questions have to be considered about the system. Then, as we know, these questions are important for the structural decisions that will affect the system and the development process. We have said before that each software system is unique. They differ one from another, but the system in the same application domain may have similar architectures that reflect the fundamental concepts of the domain, and this relates to our architecture reuse. For example, application product lines are applications. They are built around a core architecture with variants that satisfy particular customer requirements. They are built around a core architecture with variants that satisfy specific customer requirements. When designing When we design our system architecture, we have to decide what our system and broader application classes have in common. And we need to decide how much knowledge from these application architectures we can reuse. I say here, the architecture of a system may be designed around one or more architectural patterns or styles. These capture the essence of an architecture and can be instantiated in different ways. We'll see, we'll see these points in detail later. Now we'll see the architecture and system characteristics. As we have said before, there is a very close relationship between non-functional requirements and software architecture. The particular architectural style and structure that we choose for our system should depend on the non-functional system requirements. Here, we have several important requirements to be considered. The first one is the performance. As said here, we need to localize critical operations and minimize communications. Use large rather than fine-grained components. In fact, if performance is a critical requirement, the architecture should be designed to localize critical operations within a small number of communications with these components all deployed on the same computer rather than distributed across the network. This may mean using a few relatively large components rather than small, fine-grained components, which reduces the number of component communications. We may also consider runtime system organizations that allow the system to be replicated and executed on different processors. Here is the performance. We have talked about these non-functional requirements before. The second one is the security. We use a layered architecture with critical assets in the inner layers. If security is a critical requirement, a layered structure for the architecture should be used. We should use a layered structure for the architecture, and the most critical assets protected in the innermost layer with a high level of security validation applied to these layers to guarantee the security of the system. A third characteristic is the safety. If safety is a critical requirement, the architecture should be designed so that safety-related operations are all located in either a single component or in a small number of components. Like said here, localize safety critical features in a small number of subsystems. This will reduce the costs and problems of safety validation and makes it possible to provide related protection systems that can safely shut down the system in the event of failure. It's just like here the security is about the information. An example is a payment system or a bank system. The security is a critical requirements. Then we need to protect the most critical assets in the innermost layer, and we need a high level of security validation applied to all the applied to these layers. And for the safety, we may take an example of a aircraft control system. Their safety is a critical requirement. Then we need to provide some related protections. In this way, if there are some events, some failure events, for example, we can shut down the system directly, and it will be safer for controllers. The fourth characteristic is the availability. This availability include redundant components and mechanisms for fault tolerance. It means that if availability is a critical requirement, the architecture should be designed to include redundant components so that it is possible to replace and update components without stopping the system.
Ma'am, that means is it some update? Like sometimes some app gives you update for and they said they have fixed some bugs and something. So is it something like that?
You talk about availability?
Yes.
It's we can say that because it is the availability when we have to replace or update some components. We have we don't need to stop the system. We have like alternatives.
Like suppose we are using suppose the phone, like suppose I'm using Redmi, it's a Xiaomi, so MIUI. Specific time MIUI gives us an update and it says that some bugs and some issues have been fixed. So this is something like availability, right? So it doesn't shut the whole system off, but it updates. Is it something like that?
Not exactly, because here availability, it means that if we want to update a part of functionality, like what you say, your phone, perhaps we want to update the functionality of identifying. Then with this architecture, we may add two, we have an approach to be updated and an alternative. In this way, when we update one functionality, we have the alternative to replace it during a small period.
During upgradation. Okay, understood. Thank you, ma'am.
Thank you. It means the availability here is like this. And we have the fifth characteristic, which is the maintainability. It's the key point is that we can use fine-grained or replaceable components. If maintainability is a critical requirement, the system architecture should be designed using fine-grained, self-contained components that may readily to be changed. And producers of data should be separated from customers, and shared data structures should be avoided. Here are the architecture and system characteristics. Now we'll see the architectural views. In the introduction of this chapter, we have said that architectural models of a software system can be used to focus discussion about the software requirements or design. Here, will discuss two architectural views, two issues that are relevant to software requirements and design. The first one is that what views or perspectives are useful when designing and documenting a system's architecture. The second is what notations should be used for describing architectural models. In fact, it is impossible to represent all relevant information about a system's architecture in a single architectural model. As we know, each architectural model only shows one view or perspective of the system. It might show how a system is decomposed into modules, how the runtime processes interact, or the different ways in which system components are distributed across the network. For both design and documentation, we usually need to present multiple views of the software's architecture. Now we'll see different views in detail. As explained here, each architectural model only shows one view or perspective of the system. We'll see what are the general views proposed by experts. Here, we have a well-known view model of software architecture, which called 4+1 view model of software architecture. In this view model, we suggest that there should be 4 fundamental architectural views which are related using use cases or scenarios. These views are the first one, a logical view. It shows the key abstractions in the system as objects or object classes. This logical view should be possible to relate the system requirements to entities in this. With this logical view, we relate the system requirements to entities. The second view is a process view, which shows how at runtime the system is composed of interacting processes. This view, it is useful for making judgments about non-functional system characteristics, such as performance and availability for this process view. The third view is a development view. It shows how the software is decomposed for development. Clearly, it shows the breakdown of the software into components that are implemented by a single developer or development team. This view, it is useful for software managers and programmers. It's like we decompose the total system into different components. And the fourth view is a physical view. It shows the system hardware and how software components are distributed across the processors in the system. This physical view, it is useful for systems engineering, planning, or system deployment. You see, for a physical view, it's the distribution of hardware and software components. These 4 views are quite different. A logical view is for the abstractions of the key abstractions in the system as objects and object classes. Process view is how interacting processes can compose the system together, and development view is different. It's quite the contrary of this process view because it shows how the software is decomposed for development. But it's quite, it's not just contrary with the process view, because the process view, it is rather for some non-functional requirements. And a development view is for the decomposition of the software. And a physical view, it shows, particularly the distribution of hardware and software components across the processors. So here are the 4 views of this model. When we say +1 view, it means related using use cases or scenarios. In fact, this view is an abstract view of the system that can be the basis for decomposing high-level requirements into more detailed specification. This view model, it is an abstract view of the system that can be the basis for decomposing high-level requirements into more detailed specifications. It helps engineers make decisions about components that can be reused and represent a product line rather than a single system. As we have said, we have you in the last class, we have seen our figure to describe the architecture of a packing robot. It is an example of a conceptual system view. Now we'll see architectural patterns. Patterns are a means of representing, sharing, and reusing knowledge. The ideas of patterns as a way of representing, sharing, and reusing knowledge about the software system. Here is the definition of patterns. An architectural pattern is a stylized description of good design practice which has been tried and tested in different environments. So an architectural pattern, it should describe a system organization that has been successful in previous systems. And patterns like this should include information about when it is and when it is not appropriate to use that pattern, and the pattern's strengths and weaknesses. Patterns may be represented using tabular and graphical descriptions. We can see several examples. Like here, this figure describes the well-known model view controller pattern. This pattern, it is the basis of interaction management in many web-based systems. You see here, the stylized pattern description includes the pattern name, here the name, a brief description with an associated we'll see later. We may have an associated graphical model for this part, for the description, and an example of the type of system where the pattern is used. Again, here for the example, we may also have a diagram, a graphical model. We should also include some information about when the pattern should be used and its advantages and disadvantages. Here we have we can present the associated the architecture of this model from different views. Here is a conceptual view, and this one is a Yeah, this one shows a possible runtime architecture when the Python is used for interaction management in a web-based system. Yeah, you see here classic model view controller Python. We describe it like this. We use this Python to separate presentation and interaction from the system data. The system is structured into three logical components that interact with each other. The model component manages the system and system data and associated operations on that data. The view component defines and manages how the data is presented to the user. The controller component manages user interactions, key presses, mouse clicks, etc., and passes these interactions to the view and the model. And here we have provided a figure. We'll see this figure. And then for the example, we have also a figure to show the architecture of a web-based application system organized using the model view controller Python. When used, we used it when there are multiple ways to view and interact with data, also used when the future requirements for interaction and presentation of data are unknown. The advantage of this view, it allows the data to change independently of its representations and vice versa. So it supports presentation of the same data in different ways, with changes made in one representation shown in all of them. And the disadvantage of this view is that it can involve additional code and code complexity when the data model and interactions are simple. As we have said here in the tabular presentation, this figure is a conceptual view of the model view controller. Here we see that, from here we see the model components. Here, the model component, it manages the system data and associated operation like this. These operations encapsulates application state, notifies view of state changes. This model component manages these operations on that data. And the view component defines and manages how the data is presented to the user, renders model, requires model updates, sends user events to controller. Then the controller component manages user interaction, maps user actions to model updates, select views. You see, we have different user interactions like key presses, mouse clicks, and passes the, as said here, passes the interactions to the view and the component and the models like this, view selections and state change. And this figure shows the architecture of a web-based application system organized using the model view controller Python. We have the browser, then we have controller view model with the responding time and different. Yeah, you see here we have some. Yeah, in this part we have the architecture of the system. Yeah, you see in fact, this chapter is our general chapter. We cannot describe all of the generic Pythons used in software development. Here we present some selected mode examples of Pythons that are widely used and which capture good architectural design principles. Yeah. For this class, we have talked about we had an introduction of the architectural patterns where we have talked about the MVC, the organization of the MVC, the model view controller pattern. Yeah. And in the next class, we'll talk more of we'll talk more about architectural patterns in detail as we'll have some detailed example of the architectural patterns. Yeah, in this class, we have also talked about the architectural views, especially the 4+1 view model of software architecture. It's important to know what are the 4 views: a logical view, a process view, a development view, and a physical view. Then we have a scenario or use case as +1. We had also talked about the architectural design decisions. We have listed the 5 non-functional system requirements we may use to determine the particular architectural style and structure. Yeah, here are the key points for this class. Do you have some questions for this part? Okay, thank you.
Have a nice day.
Bye, everyone.
Bye.
Have a
See
nice
you.
day. See you.